Alright, so let us look at this problem. Consider the problem, minimization problem, that we want to minimize the distance between Ax and B. So if B is already in the column space, then the distance between them is 0. So I can solve the system Ax is equal to B, there is no problem. So if B belongs to column space of A, then Ax is equal to B has a solution, and the value of a star, is 0, and there exists an x naught belonging to column space of A, fine, which gives us Ax naught is equal to B, fine. So I'll get something. Now if B does not belong to the column space of A, so if B does not belong to the column space of, this is my column space of A, B is outside, I am supposed to look at something which is perpendicular here and then proceed, fine. So I am trying to find out the nearest vector in column space of A, alright. So now that we have proved the Gram-Schmidt process and so on, so let us do that part. So what I know is that this is a subset of Rm. So we know that Rm can be written as column space of A direct sum null space of A transpose. Recall the idea that I had Rm here, so fundamental theorem of linear algebra, So I had this line with me, this was 90 degree, this was null space of A transpose I think, and this was the column space of A, fine. So I can take a basis of this. So let u1, u2, uk be an orthonormal basis of null space of A transpose, fine. We can extend it, to form a basis of Rm. Further, apply Gram-Schmidt's application will give an orthonormal basis, say u1, u2, uk, then uk plus 1 till um, where uk plus 1 to um is an orthonormal basis of column space of A. Why you can do it? Basically because look at this, what we are saying is that column space of A is perpendicular to null space of A transpose, alright. This perp is there, therefore perpendicularity comes, and therefore we can do things, alright. So this is important for us. So what we are saying is that I have a vector B, I decompose B in terms of column space, some element of column space and something with the null space. Is that okay? So I am doing that. So because of this part, now I can say that there exists a unique, so B belongs to Rm implies B is equal to linear span of u1 to um. So this will be equal to some alpha I ui, I is equal to 1 to m. I can write it as I equal to 1 to chem alpha I ui plus summation j equal to k plus 1 to m alpha j uj. So this part belongs to null space of A transpose and this belongs to column space of A, alright. and this is unique, that is important, alright. So, I am writing B as fine as some y plus v, where y belongs to column space of A and v belongs to null space of A transpose, and these vectors are unique vectors and orthogonal. All right, y and v are orthogonal. This is the way the graph is, and that is what the fundamental theorem of linear algebra tells us, that they are orthogonal. Fine. So, therefore, when I am looking at this thing, so if I want to look at the minimum over this Ax minus b, minimum over x belonging to Rn, then this is attained by, alright, I have to take something from x, so I have to take y belonging to the column space. So, this is attained by y minus b, alright. So, y is the vector which minimizes it, which minimizes a star, alright. But what is y? Y is element of column space, so it is nothing but this. So, if I can write in terms of ordered basis also, but what we are just saying here is that, or in this problem is that, since y belongs to column space of A, implies there exists x naught belonging to Rn such that y is equal to Ax naught. Alright, this is what it is. Fine. So, now we already know that. So, what we are saying here is that I have a solution of a star here, which is x naught. I have to prove that A transpose Ax naught is A transpose B. Alright, so let us try to prove that. To show A transpose Ax naught is equal to A transpose B. So, let us do that part. So, let us look at what is A transpose Ax naught. A transpose of Ax naught, we just saw it was, alright, Ax naught is y. So, it is just y for me, which is same as A transpose of what is y. So, y if I look at from here, fine. So, y from here is nothing but b minus v, which is same as A transpose of b minus A transpose of v, which is same as A transpose of b minus, what is A transpose of v? V belongs to null space of A transpose, and therefore, A transpose of v is 0. So, I get it as A transpose of b. So, therefore, if x naught is a solution of a star, then x naught satisfies A transpose Ax naught is equal to A transpose of b, or x naught is a solution of A transpose Ax is equal to A transpose b. So, I have proved one way. Now, let us prove the other way around. Now, to show, now let us assume that x naught is a solution of A transpose Ax is equal to A transpose b. To show Ax naught minus b, this is equal to minimum over all x belonging to Rn norm of Ax minus b. This is what I have to show. Fine. So, let us try that out. So, what does it mean to say that x naught is a solution here, and what does it mean to do things here? All right. So, this part implies that, look at this part nicely, it says that A transpose Ax naught is equal to A transpose b, I wrote inverse, A transpose b, and therefore, I look at A transpose of Ax naught minus b is 0. Fine. Now, from here I want to relate these ideas here. How do I do that? Fine. So, I am looking at minimum of Ax minus b. So, let us look at norm of Ax minus b, this whole square, be careful. So, we are going to write it as norm of Ax minus Ax naught plus Ax naught minus b whole square. So, the way we have been decomposing, what we will get here is this will be equal to norm of Ax minus Ax naught whole square plus norm of Ax naught minus b whole square plus, since everything is real here, so it will be 2 times inner product of Ax minus Ax naught comma Ax naught minus b. This is what we will have. Fine. That is the way we will be decomposing, that u and v are there. Then if I write u plus b comma u plus v, the norm of u square plus norm of v square plus 2 times inner product between u and v. All right, that is what we have been doing. So, let us look at what is this. So, this is equal to, if I want to look at, is by definition is Ax naught minus b whole transpose Ax minus Ax naught, fine, which is nothing but, or I think I have written it the other way around here. So, let me write the other way around. All right. So, this is same as Ax minus Ax naught transpose Ax naught minus b, because xy is same as yx for us, because this is same as y transpose x, which is same as x transpose y. Everything is real. If it was complex, then you can look at complex conjugate, you will get the same thing. So, this is same as, just look at this part, it is x naught. So, this is equal to x minus x naught transpose A transpose into Ax naught minus b. All right. So, this is equal to, if you look at it, is x transpose A transpose minus x naught transpose A transpose. So, I am taking A transpose on the right and then writing here, fine. So, this is what I have, x transpose A transpose minus x naught transpose A transpose, x naught transpose x naught I have taken it as separately here, fine, and then A transpose. Now, we have been given that this thing is 0. Look at here, it is given that this is 0 and therefore, this is 0. So, what we are saying here is that this part is 0. Now, when we say that this part is 0, what does this imply? It means that, look at this part, Ax means elements of column space of A, fine. So, any column is any vector here minus this. So, I am saying that any vector, so this if I look at, so I have a plane here which is the column space of A. So, Ax is any vector here that I am not bothered about, Ax naught is some fixed vector here. Look at this, this is my vector Ax naught minus b. Then we are saying that this vector is perpendicular to everything here, fine. And what will that imply? If it is perpendicular to everything, it means that that must be 0 as such, fine. So, therefore, what we are saying here is that this is greater than equal to, this is 0. So, norm of this is this. So, norm of this is greater than equal to the norm of this. So, therefore, what I get is that norm of Ax minus b whole square is equal to norm of Ax minus Ax naught square plus norm of Ax naught minus b whole square. So, which is greater than equal to norm of Ax naught minus b whole square. So, the minimum is attained at x naught itself, all right, whatever you do, because if you change any x, you get something extra here, fine. So, this is what we wanted to prove. Look at the thing here. It said that if x naught is a solution of A transpose A equal to this, then x naught is a solution of A star. So, x naught is the one which gives you the minimum. Is that okay? So, we have been able to show this also. So, what I would like you to understand now is there are two things here. One is that if you want, so want one, if you want to solve Ax is equal to b, if b belongs to column space of A, there is a solution using Gauss-Jordan elimination method, all right. I already have a solution, fine. If B does not belong to column space of A, then no solution, but we can find the nearest vector x naught belonging to column space of A such that nearest vector such that norm of A x naught minus B is minimum over x belonging to Rn norm of Ax minus B. And how do we do that? And to get this, what we are saying is that just solve A transpose Ax is equal to A transpose B. So, in place of solving the system Ax is equal to B, I need to solve the system. So, solve a new system, all right, fine. Now, what the QR algorithm says, QR algorithm gives way of solving it, because if you, so what we had was A was equal to QR, fine. So, if I want to compute A transpose A is nothing but QR transpose QR, which is same as R transpose Q transpose QR, which is R transpose R, all right. R was an upper triangular form, R and upper triangular form. So, R transpose is lower triangular, fine. So, I just have to solve the system R transpose R is equal to A transpose B, I just have to solve it. So, again it is in some sense I am looking at a lower triangular and an upper triangular. I am looking at this and I am trying to solve the system this, and we have already know how to solve the system LU of x is equal to B. So, we are doing the same thing, this is a new B and I just have to solve the system as we did earlier, fine. So, there are a lot of ways of doing it, understand it. If A transpose A, if A is full rank, if A transpose A is invertible, which is same thing as saying that A is of full column rank, then I can compute the A transpose A inverse, because in that case Q transpose Q is invertible, everything is nice. So, if A transpose is invertible, then this will imply that x is equal to A transpose A inverse A transpose B, fine. If it is not invertible, then we can solve it using what is called a pseudo inverse or the Moore-Penrose inverse, but that is not in our syllabus, all right. For us the syllabus is that only to pick those A's for which A transpose A is invertible, all right. So, let us go to the one of the first example that we looked at. I do not remember the exact question there, but the idea was the following, that we had to find the foot of the perpendicular from the point 1, 2, 3, 4 on the plane generated by the vectors, I think it was 1, 1, 0, 0, 1, 0, 1, 0, I think 0, 1, 1, 2, I think this is what it was, all right. So, we had got it by one method, fine. So, plane generated by the vectors this. So, we had got it using the idea that this thing is generated by the vector by the x minus y minus z plus 2w was 0, I think, let me check it, 1, 1 is 0, 1, 0, 1 is 0, 1, 1 and minus 2, yeah, 1, 1 minus 2, all right. So, we looked at this, from there we got the normal of the vector, normal of the plane as 1, minus 1, minus 1, 2. Using this, what we did was, we looked at 1, 2, 3, 4 minus projection of 1, 2, 3, 4 on this vector whatever it is. So, V I write it as this on this. So, this gave me, so what we are doing is look at this. So, again I have a plane which is generated by x minus y minus z plus 2w is equal to 0. I have the vector 1, 2, 3, 4 here. I drop a projection here. This is my projection vector, projection of 1, 2, 3, 4 on this. Fine. And we looked at this minus this. So, this was the vector, this is the projection, and this is the one that I am computing. So, I computed this. So, once I computed this, I could get this point which was on the plane, all right. The other way will be to look at this itself and proceed, fine. So, the other way will be look at the orthonormal basis that spans x, y, z, w belonging to R4, so that x minus y minus z plus 2w is 0, all right. So, to do that I can apply the Gram-Schmidt process, Gram-Schmidt's. So, I can take my w1 to be is equal to 1, 1, 0, 0 divided by root 2. I can take v2 is equal to 1, 0, 1, 0 minus 1, 0, 1, 0 inner product with 1, 1, 0, 0, 1, 1, 0, 0 divided by 2, which is same as 1, 0, 1, 0 minus 1 upon 2, 1, 1, 0, 0, which is same as 1 minus half is half, 0, so minus half. So, this is 1 and 0. So, therefore, W2 can be taken as, so I can take W2, so just look at this part, I can take out half outside, it will be 1 minus 1, 2, 0. So, I can take W2 as 1 minus 1, 2, 0 divided by 6, the square root of 6. Similarly, compute W3 and then that vector, the vector, the nearest vector, then the nearest vector will be equal to, so 1, 2, 3, 4, inner product of this with W1 plus inner product of 1, 2, 3, 4 with W2 plus inner product of 1, 2, 3, 4 with W3. So, I would like you to check that these three will also give you the same answer as this, all right. So, these two answers are going to be the same, fine. We'll try to understand them. So, we would like to look at this part. So, let us recall one theorem that we had, and then from there I want to say that this is the one that I am looking at, fine. So, what I need is that these are the components that I am looking at. So, I have to multiply by W1 here, W2 here and W3 here to get the answer, all right. The nearest vector will be a vector, not a scalar quantity, fine. So, I have to write that. So, let us try to understand what it is. So, if I want to write it, I can think of this as I have a vector here which is 1, 2, 3, 4, all right. I am looking at W1, is for me it is a column vector. So, it is a 4 cross, so what is this? This is a 4 cross 1 vector, W1 transpose. If I look at this part, this together gives me a 4 cross 4 matrix, fine. Again, if I look at just W2, W2 transpose, this also gives me a 4 cross 4 matrix, and similarly this part also gives me a 4 cross 4 matrix. So, therefore, if I want to look at, so consider W1, W1 transpose plus W2, W2 transpose plus W3, W3 transpose. It is a 4 cross 4 matrix. Fine. Now, this is a 4 cross 4 matrix. I am just write like this, and let us multiply this with 1, 2, 3, 4. What do I get? Fine. If I multiply this, what will I get? I will get it as W1 W1 transpose times 1, 2, 3, 4 plus W2 W2 transpose of 1, 2, 3, 4 plus W3 W3 transpose 1, 2, 3, 4, which is same as, alright, which is same as, this is a scalar quantity, this is also a scalar quantity, this is also a scalar quantity, and this scalar quantity is nothing but this scalar quantity is this, and this is same as this. So, we have been able to write, if I write this as a matrix and then multiply with the given vector, I am just saying that this part is nothing but the projection part, alright, fine. So, I want you to understand this part, which is very important. What we are trying to say here is that in place of computing this separately, I can just compute the matrix, alright. This matrix is called matrix or projection matrix. So,